Welcome, JuliaCon. Woo!
It's great to be here, everyone. Oh, is this? All right. So, this is the 11th one or the 12th one. I'm kind of losing
11th.
track. This is an awesome venue. It's great to be here with everyone. We're going to take a few minutes to talk about what we're doing, at the company at JuliaHub. We started out by building a programming language, as some of you know, maybe. And we've increasingly sort of gone up the abstraction chain, building lots of innovative things for modeling and simulation. So for those of you who might not have seen this picture, this is how we like to talk about what we do. At the bottommost layer, the foundation is the community. It's all of us here. We all work on this shared and common vision for Julia. And we have this amazing open source ecosystem and packages. But as a company, in addition to that, what we do is we build JuliaHub as a cloud platform to run a bunch of modeling and simulation applications. And now we've gone up the abstraction chain, building products for modeling and simulation. Many of you have seen Pumas, which is a company that spun out and is something that we're very closely involved with. JuliaSim, which is what we're going to talk about in a little bit. Chris is going to talk about a lot of it today. And then we have Gary Mansouri from Boeing, who's going to also talk about sort of model-based design. And we have a lot of interesting things around JuliaSim that are coming up. The third one is Cedar, and we have a few talks at the conference about that as well. So this is sort of how we're building products as a company. I just have this one technical picture. I thought that people out here who understand compilers or who like working with compilers would sort of appreciate it. That the world of modeling and simulation has been these kinds of bespoke systems that are like hand-hacked with all kinds of horrible in all kinds of horrible different ways built over the last 40 or 50 years. And one of our goals is to use all the beautiful Julia compiler tooling and abstractions and have a lot of different front ends, not just Julia, but whether it's a SPICE front end or a pharmacometric front end or a systems modeling front end, right? So you'll see a lot more of these evolve, leveraging a common backend that we've all built together. If you want to know more about this, find Keno or Chris later on during the conference. We have about, I think, 24 talks, or JuliaHub staff is involved in about 24 talks at JuliaCon. Many of these talks are actually in partnership with community members. I actually have, there are 3 pages of talks, actually. So these are all the talks. I'm not going to sort of wait for these. Without further ado, we'll have Chris talk about JuliaSim next.
Yeah, thank you very much. So JuliaSim is Julia really taken to industrial modeling and simulation, right? Because you might know a lot of companies out there, like, there's like the Modelica community with like the things like Dassault Systems. You have all the things that ANSYS builds, right? And there's also this company that starts with an M, which we won't finish, right? And so there, but the thing that is there about a lot of modeling and simulation tools is that they are written as bespoke software, right? You have one thing that does computational fluid dynamics, you have one thing that does chemical process modeling, and they can't connect. And when the moment you try to connect all these, you have issues, right? And so the idea was, could we build a modeling and simulation platform with a common compiler, a common core, so that way we can optimize cross-domain modeling and make it work in such a way where we can deploy it to real systems and send it off as flight software, automotive software, and all these applications, right? It's a lofty goal, but this is what we've been building towards with JuliaSim. And so JuliaSim has a whole stack here where we have these graphical user interfaces and VS Code extensions that make it so that way someone can drag and drop and build a very high fidelity model and then send this code to a system where they can then build out custom deployments with custom drivers and make it so that way all of the things that we do with machine learning integration, all the things that we do with all this like binary generation, all of that works as one stack that is in changing the way that we are building the models of tomorrow. And so here's a view of JuliaSim, and we'll be showing a lot of people things as is coming out, right? In the next year, we're really going to be showing a lot more material. So stay tuned and subscribe to our YouTube channels if you want to see all the things coming out on JuliaSim. Here you can see an early view of the graphical user interface. You can see that you have a drag and drop editor, and from this drag and drop editor, which works in the cloud, you can grab all of these different model libraries, right? So you have one of the key things that we've done with this form is that we have analysis components. So you can say, not just, I want to just simulate, I want to make a plot, but I want to run an optimization. I want to automate the discovery of new physical elements using data that I have. And I want to run a gigantic parameter search over a GPU cluster. And all of this can be done using this cloud-based modeling and simulation tool that we've been developing. And so one of the key things that we've been adding to it, too, are these built-in libraries, right? So there'll be talks on different libraries here. For example, we have a talk about the JuliaSim HVAC library, which is a high-fidelity two-phase flow system modeling the exact properties of these, a lot of refrigerants. There's a model library, or there's a library on JuliaSim batteries, which will be talking about different electrochemical models and how those are then used to be able to build models of battery packs that can be connected to other systems. There are multibody components that we've been developing as well, and there's all these other talks that you should go to. So, there's JuliaSim itself is not just a system for building models, but it also has a lot of these industry-focused, high-fidelity models that are pre-built, so you can just drag and drop in a digital twin of an HVAC system with a digital twin of a battery, and then build out this entire model of here's an electric vehicle, and what will be the what kind of battery will I have? What will the thermals be, and how will that affect the car design? Can all be built as one composed system. Right? And now there's going to be some talks on this new piece that we're releasing here, this JuliaSim modeling language. Right? So the JuliaSim modeling language is the language that it's a declarative language which is underneath the way that the GUI is built, and it has a very nice property in that everything that you do in the GUI shows up also in the JuliaSim language. If you make a change to the code of the language, it makes a change to the GUI display. You make a change to the GUI display, it also goes back. So we have this round trip ability between the way that you use code and the way you use graphical user interfaces. Because we have an idea that these graphical user interfaces of the past should be of the past, because everyone today is using some form of coding, and so you need to have code and graphical user interfaces live in the same world. And that is what we're really trying to make sure we can do to change this industry. And one of the other pieces involved with this is JuliaSim Studio, right? So JuliaSim Studio is a set of extensions for VS Code, and what you can do is you can take this model that you've built using the JuliaSim modeling language and the graphical user interface, and you export it to Julia Modeling Toolkit code. And so if you know Julia Modeling Toolkit, if you've been working with our open source tools, you get a full representation of your model, and then you can say, you can write your drivers, you can use the new JuliaC tools, and you can create, you can take the model code that you have and the analysis that you've done in the graphical user interface and create bespoke code for then the deployments to real-world devices. Last but not least, we are integrating the scientific machine learning tooling in every part of the stack. So you can see, for example, here's a demonstration we have of the digital twin generation, where you can build a physical model where you have like a real HVAC system, a real battery, and you say, maybe I use ideal physics for one of these pieces. And what you can do then is you can integrate a neural network into this process and tell it to train this neural network to improve Oh man, there's definitely something going on there.
I think the planes came out a little earlier than when Gary was supposed to talk.
So that's JuliaSim, right? And we're really working with the industrial modeling and simulation world and really building out a new tool that can make sure that we can bridge this gap between GUI to code to embedded devices. And so I'm really happy to have Gary here from Boeing, who will have a quick question and answer session to be able to describe, what are some of the things that Boeing is looking for, and just as one of these people to understand, who JuliaHub is working with in order to make sure that Julia process this gap from being a great language to being a great language for industrial computing. So Gary, we're going to have a few questions for you, and afterwards, if this question and answer session, if you find it interesting, we'll have a birds of feather session on safety critical software, which anyone can join, and that'll be right after these sponsor talks. So question number 1 to Gary: how does one go into a career on model-based design? So how does one step away from, if you're an academic here and you really want to work on, putting the software onto an airplane, how do they do this?
Thanks, Chris. First, I'm more excited than Chris, but I'm not showing it. So good morning, everyone. Very nice question. How does one go about a career in model-based design? So there are different paths. Perhaps the best path is to be good at something that you already do, whether it's modeling battery systems, electronic systems, dynamics of some sort, could be power systems, hydraulics, vehicle dynamics, whatever the path might be, even mechanical design. So be good at that. Then model-based design applies the whole set of processes to make the design come to reality. So model-based design is not modeling. It's using modeling via a process so that basically we conduct systems engineering with that modeling process. And that's what model-based design really means. And people tell me all the time, well, Gary, we have been doing modeling for 40 years. Why is this new? What is this? And so what is this about is to use modeling as a means of debugging, if you will, to refine your requirements early up front so that your design becomes virtually debugged before you actually design it, before you have the physical design. You heard Chris talk about the digital twin. It's really having a digital twin that represents your actual design such that your design is meeting very high confidence before it's done being designed. So how does one go about making it a career? Be good at one specific topic that you're good at, whether it's, again, battery design or dynamics. Understand the systems engineering with model-based processes, and then apply to that, and then you become the go-to person. That's probably the best answer I can give.
That's a great answer. Now, the next question we have is, how is modeling and simulation used in Boeing? What are the types of things that get modeled? And what is the downstream effect on an airplane that is made?
Well, that's a very big question. So modeling and sim is used very, very broadly and extensively at Boeing. Pretty much almost anything you can think about on an airplane has been modeled to some extent. You have the fuselage of the body of the airplane, the wings, that are now composite. They all have been modeled. Then we can go into the structures of the airplane that has already been modeled. So that all basically CATIA, using tools like CATIA with CAD, CAM design. Then you go into the systems aspect of the airplane where you talk about avionics, flight controls, actuation, power systems, ECS, which is environmental control systems. That's the cabin air and all that. And basically everything else. All of those systems have been modeled very carefully. The application of model-based design comes in where we actually use models as requirements so that we catch everything very carefully, not with a shall statement, but rather with a descriptive dynamic model. And so instead of having a switch written as a shall statement, you can have a transfer function that describes that switch transition. And so, but going back to the question, those are just the airplane design. Then there's all we're talking about the system installation, how all the equipment and parts and pieces come together. The flow and the efficiency of that has been modeled. The production line, the flow of that has been modeled. The finance, parts assembly, parts delivery, the optimization of how that gets delivered has been modeled. And going forward in the future, even production system and the finance part of the company is being modeled. So everything basically is going through modeling and sim.
Everything is a model. And now, next question is, why does Boeing use model-based design? Can you quantify its effect on downstream processes, estimate things like dollars saved or development time reduced? And what can you give any examples of early detection of potential issues?
Sure. And that's a really, really good question. And this is basically my role at Boeing as a technical fellow. Model-based design, and this is based on data in the industry for the last 20 years, primarily from the automotive industry. The aerospace industry has been somewhat behind because of all the regulatory aspects. But model-based design, based on industry data, you're talking about approximately 30% savings in schedule time and about that much in cost reduction. And that's very significant. So if you think about the overall traditional development cycle, you're talking about cutting off about a third of that, also about a third of that in cost. But the most important aspect of that to us, to Boeing, is really the first pass quality, is improving quality, is getting something that when it comes out has significantly less problem reports. You can think about cars when you have a car that gets a recall. So it's to avoid things like that, minimize that. That's what we call first pass quality. And by the way, quality leads to improved safety. So, so we use it at Boeing to improve our first pass quality, but to stay competitive in the market, we have to utilize new technologies and new processes. And model-based design is an enabler for that. It's a way to using model-based technologies so that you have higher confidence in your design before you have the physical system in place. That's the answer.
Yeah, and there's a reason why people are saying like Boeing is a software company, right? Because a higher and higher percentage of the savings are coming from software developers like you. One last question we have here then is, what is the main thing that engineers need to know in order to understand software development for safety critical environments?
Okay, this is a very big question, and it's a very important question. So let me ask you this, and when you think about safety, what drives safety? One word I'm looking for. Like, what leads to better safety? Anybody raise your hand? Any? Accidents lead to lessons learned, but what I'm thinking of is an attribute that you use in your design to lead to better safety. Redundancy. Redundancy is a very good word too. Quality assurance.
I think we had someone with testing.
Get it, Boeing. You're welcome. So quality assurance. Now, all of those answers were correct, but quality assurance is what leads to safety critical environment. It's all about the quality. So how do we get to a quality assurance environment? It's really two things. The process has to be very well defined. So you have to have a very well defined process. That means you can just start coding or modeling. You have to follow a very vigorous process. And then you have to have a very, very strict set of requirements. And both of those are required before you start doing your modeling. So when you talk about flight critical, really the number one thing that comes to mind is quality assurance. And quality assurance, and that's your prize, is again driven by process and requirements. So there are two different processes that we follow per regulatory aspirations or requirements. One is DO 178C. That's for all software that is going to be used for flight. And there are different tiers of safety, different tiers of usage. Flight critical would be 1 or A. And then there is the DO 331, which is model-based software that's derived from models. So both of those two processes we have to follow as part of the regulatory authority requirements. And the fundamental starting point for that would be to have a very clear process that is captured, that we can follow and demonstrate that we follow that process. And that's what quality assurance comes about. And basically, it's a very extensive checklist of items that we have to do that ultimately includes qualification of tools. That means you freeze your tools for that. So that's a very high-level answer to the question. This question, I can spend about a week in 8-hour days in different segments to answer. But I hope that gives you kind of an insight as to the extensive process and work that goes into creating safe flight critical software.
And we'll have a whole birds of feather that'll be discussing about, what it is to be using Julia now within these, safety critical environments, right? Because we've been working with folks at Boeing, but also with groups like Pumas. We've been working with the FDA, right? As you know, certain therapeutics have been, fully processed, and the clinical trials have been done with Julia. And so, what does it mean to be programming in these environments, and what does it mean to be programming for these environments? If you're very interested in, how these open source tools have been growing, and the industrial products that have been developed on top of them are reaching these standards, we'd be happy to chat with you more on during this Birds of Feather. So,
or if you're just curious, right? Like if many of you here are software developers, maybe have not worked with modeling or model-based environments, and if you got curious by listening to Gary, I suggest join us at 10:15, the Birds of a Feather session, and all questions are welcome, right? Like if you have anything that you'd like to learn, please come there. I know that working with Gary, I've learned a lot about what it takes to build software that you can trust. And so I request all of you who are curious to join us at 10:50.
Thank you, Viral. And thank you all for your time.
Thank you. Right.